bipolar junction transistors are very useful and they have led to modern computers. They are basically two diodes connected in the appropriate fashion to generate what is known as a transistor. So they have, as I said, two junctions. It could be NPN transistor or a PNP transistor. So this is two junctions. There's a NP junction and there's a PN junction. So that's two diodes. Same here. Okay, here's the schematic of the NPN transistor. So N, P, N. One of these N is called as a collector. The other one is called the emitter. And the middle one is called the base. We can draw a similar diagram for the PNP. So P and P. Again, we would have a collector, an emitter, and the middle one is the base. It's often abbreviated as C for the collector, E for the emitter, and B for the base. The circuit symbols for these are as follows. Here first is the NPN. The VB indicates as the base, VC collector, and VE emitter. Now, how do you distinguish from the collector from the emitter is that you would put an arrow showing the direction of the current for the NPN. Okay. Similarly, we can do a diagram for PNP. Collector, emitter, base. So VP, PE, PC. And here we'll show the arrow in the opposite direction of the emitter. Okay, so the way this circuit looks like is it basically looks something like this. Okay, it is sort of semicircular on one side and flat on the other one. And you can look at the spec sheet of this and you can make sense of the three leads. This one I'm showing is 2N3904, which is a NPN transistor. If you read the spec sheet, you'll see that the one on the flat side, the one on the left, when you're looking at it from this way, on the other end would be the emitter. This would be the base. This would be the collector. And there is also a test based on using a multimeter in the voltmeter mode to figure out what are these leads without actually having referred to a spec sheet. And you can try to do this intuitively, or you can look at videos online of how this is done. That is, identify CBE without looking at the spec sheet. So here in a BJT or a bipolar junction transistor, emitter is more heavily doped than the collector. And if it was not done like so, then you would not really have current flowing in this, because then the collector and emitter would serve the same purpose. Okay. The base is actually a thin layer, and that's why I did show this middle layer slightly thinner than the other two layers. Now here in this course, we'll pretty much focus on the NPN transistor just because it's more popular, but the PNP is very similar to the NPN. Everything I do here for the NPN is applicable for the PNP. Okay, so let's look at the symbol diagram for the NPN transistor. So we have VB, VC, VE, and as I said, this is N, this is N, this is P, and then we usually denote this with the symbol showing the direction of current flow. Okay, now the way the current flows is there's a current flowing through IC, there's a current flowing through IB, and that happens because PB is positive related to the emitter, and then VC is also positive with respect to the emitter. So because of that, current will flow in the direction shown. So the current from the collector and the base flows through the emitter like so. So we notice from this that BE is forward biased. That's because the B is, remember, it's the P, and so it's connected to the positive terminal, so it has to be, and of course the E is connected to negative, so it's forward biased. So this is known as the voltage across VBE, which can also be written as, let me write it down here. This voltage is VBE, which is simply VB minus VE. Okay, the second thing to note is that VC, the base and the collector, is reverse biased. Okay, the base, this is connected to the positive, and so is P. So what you would expect is that there won't be any flow of electrons from C to B, but it does flow from C to E and B to E. Now, electrons do flow from E to B. So E to B, which means that current flows from B to E. So flow of current is opposite to the flow of electrons. Okay, let me write that down. So electrons flow from E to P, or current flows from P to E, and that is shown in the figure. Also for the NPN and also for the PNP, the emitter current is the sum of the collector current and the base current. Another thing which is a property of the transistor is that the current in the collector is beta times the current in the base, where this number beta is about 100. Now this happens in a certain mode called the active mode. And we'll talk about the active mode in a bit. But what's happening in the active mode is that a small flow IB leads to a big IC. So the collector current is 100 times the current in the base, and this is how the BJT can be used for control. If you can have your control system modifying IB, then it can lead to a huge change in IC because there's a proportionality which is of the order of 100. And so think of this like a knob which is used to change the flow of, say, water. So when you turn on the switch to let the valve open up, there's a huge flow in water, right? And that is your IC, but you only require a small force to turn the knob. That leads to a huge force coming out. So this is somewhat like a tap in your house or a check valve. Okay, now let's go a little bit deeper into the working of a junction transistor. I briefly mentioned about the active mode, but then there are actually three modes, and it's important to know all these three modes. Three modes. Number one is the cutoff mode. Number two is the saturation mode. Number three is the active mode. Okay. And just like we have plots for the diodes and resistors, this is the plot which is often used to describe the working of a BJT. It's a plot of the potential between the voltage between collector and emitter on the x-axis, the collector current on the y-axis, and the other parameter is IB. So what is done is different. The plot is done as different IBs. Okay, so here is third one, fourth one, and this is for a specific IB. So each of these lines have a specific IB. Now, when we look at this region is known as the saturation region. In the saturation region, IC is less than beta IB, or in other words, you don't really get that tap or fluid valve like effect. Okay, you don't really get the magnification, so you would not really use the BJT in the way that you control a tap to control the flow of water. There's another place which is important, which is this part of this plot. This zone is known as the cutoff region. Here, the currents in IB and IC are close to zero. So really, again, you don't have the benefit of the BJT, which is small IB will lead to a great change in IC. Okay, but you should know that. And then we'll see that these regions are also used for something in just a bit. The other region, which I've not highlighted, which is this part, which is shown in white, is the active region. And this is the region of most interest for us in control. Here, we see that we can use this current IB as a control signal to control the flow of IC, core of charge in the collector. So I'm going to draw a circuit, like a very basic circuit for a transistor, and then we'll see how these modes are used effectively for controlling something. So let's draw the NPN transistor first. Connect it to a battery. Then connect the collector to a resistor. So this is a collector connected to a resistor, let's say RC. Let's call this RB. This is clearly VC. So it's connected to the collector. Let's call this voltage as VP. This is showing that's an NPN transistor. And let's say that we want to measure the voltage, but this is the ground, and we want to measure the voltage between this point and the ground. So V0 or V out. Okay, normally VB is your input. Remember the check valve, by controlling V in, you can control the current flowing in base, and that should have an effect on how IC and IE change. Okay, now the two things you want to remember is there is the V voltage between C and E, VCE, and then there is a voltage drop between P and E, VBE. Okay, so now let's switch to the modes. Number one, cutoff mode. In cutoff mode, the currents are 0. Here, VBE, which is the potential drop between the base and the emitter. Remember, the base is P and the emitter is N. So think of it like a diode, base, emitter. And remember what we said about a diode. A diode can be forward biased when the voltage drop is 0.7. So it needs to be 0.7 to be conducting, right? But because it's cutoff mode, VB is less than 0.7. So if this happens, then the net result is that V out is simply VC. So in the cutoff mode, the output voltage is whatever the supply voltage is to the collector. Okay, now, the other mode is the saturation mode. In the saturation mode, the current I is greater than 0, IC is greater than 0, VBE is greater than or equal to 0.7. In other words, it means that you are changing the voltage in B such that the phase emitter is greater than 0.7, which means that it is conducting. And that's why the current IB is not 0, but it's greater than 0. When that happens, V out, which in this case is nothing but the voltage from C to E, is about 0.2. That is actually the potential difference between C and E. We must C and E are both N and N junctions, and that is, you can approximate that to be 0. So in ideal case, if there was no potential drop, it would be 0, but 0.2 can be assumed, which is in real world it's 0.2, is very close to 0. So what you can do with a BJT is you can use a BJT as a switch by cycling between cutoff and saturation. Okay. Why so? Well, what we're trying to do here is we're trying to control VB or V in such that the voltage out is controlled. By being in the cutoff mode, by setting the VB appropriately, and this will be clear when we do a problem, V out here is VC. So this V out is this VC in the cutoff mode, but in the saturation mode, by changing VB, we are effectively able to get V out equal to 0. So this BJT shifts from going from VC to 0 as we change B or VB. And that's how we can use it as a switch. If you connect, let's say, a light emitting diode here. So connect to an LED, then you'll see that the voltage across the LED will be either VC if it's in cutoff, if the BJT is in cutoff mode, or 0. And that way you can get the light emitting diode to be either bright or dim. Okay. There is a question where you will be analyzing this circuit for your homework, where you'll actually build it using Tinkercad, and then you'll vary the V in and look at the corresponding output at V out, and hopefully by doing this experiment, you get an intuition of how V out changes as VB is modified. Okay, the other mode is the active mode. In the active mode, the following is true. We have IB, current in the base is greater than 0. IC is greater than 0. VBE, this is the diode, which is between B and E, should be greater than 0.7 volts, which means it's conducting. And the last piece is that the V out, which is also VCE, is between 0.2 and V0. Sorry, VC. Remember, VC is the voltage which is applied across the collector. Okay, so what's going on here is that by changing VB, which is equal to V in, we are able to vary V in from, vary V out from 0.2 to VC. And so if you can vary the voltage linearly from 0.2 to VC, then we can use the bipolar junction transistor to supply, say, some voltage to say a motor or a resistor, a constantly increasing, changing voltage if you need to do it that way. So in this mode, it's also known as a linear amplifier. So BJT is a linear amplifier in the active mode. Okay. And then I forgot to put this. There's also some other relations which you also hold. One of them being that IC is beta IB, and then IE equals IC plus IB. So this second relation is all true no matter what. The first one is only true for active mode. This one is always true, but this is only true for active mode. Okay, so again, in our homework, you will basically create this circuit and analyze how to get this transistor in the active mode, and you will do the experiment in Tinkercad. Okay, now let's see how all this can be applied to solve problems. So we'll solve problems by hand for a system which is for a junction transistor system, and that'll give you an intuition of how to use these equations.